Folks, welcome to presentation on signal flow graph representation. We see some properties of signal flow graph. Signal flow graph is applicable only to linear time invariant systems. Signal flow graph flows along branches and along arrowheads associated with the branches. The signal gets multiplied by the branch gain or the branch transmittance when it travels along it. And the value of the variable represented by any node in an algebraic sum of the signals entering at that node. So if you really see a signal flow graph in figure 6.6, you have a branch x0 to x1 which is designated by 1. Likewise, you have several branches, and then you have concepts like source nodes. The node having only outgoing branches is known as the source or the input node. Sink node, the node having only incoming branches is known as the sink node or the out node. A node having incoming and outgoing branches is known as the chain node. A forward path. A path from the input to output is defined as the forward path. So x0, x1, x2, x3, x4 and x5 is one forward path. x0, x1, x3, x4 and x5 is another forward path. x0, x1, x3 and x5 is another forward path. x0, x1, x2, x3 and x5 is another forward path. Then we have what are called feedback paths. Path which originates from a particular node and terminating at the same node, traveling through at least one other node without tracing any node twice is called as a feedback path. For example, x2, x3, x4 and x2 is a feedback path. A self loop. A feedback loop consisting of only one node is called self loop. For example, T3 at x3 is a self loop. A self loop cannot appear while defining a forward path or a feedback path as node containing it gets traced twice, which is not allowed. Path gain. The product of branch gains while going through a forward path is known as path gain. So, for example, for the path x0, x1, x2, x3, x4, x5, it is 1 into t12 into t23 into t34 into t45. This can also be called as forward path gain. Now you have the concept of non-touching loops shown in the diagram figure point 6.8a. You have having three non-touching loops. One is x1 to x4. Other one is we have loop L1, x1, x3 and there is a feedback path. Then you have the other one x1, x3, x4 and x1 and then x1 and L2 and x4. So in this, there are only two non-touching loops. Now if you see figure 6.8b, you have three non-touching loops. So this is the concept of non-touching loops. And we have concept of loop gain. So supposing I have a loop x2, x3, so we have minus g2 into h1 as the loop gain. Supposing I have a self loop, then minus 5 is the loop gain for L2, and for the last one it is minus 4 into 8, so it should be minus 4 into minus 2, that is minus 8. So methods of obtaining a signal flow graph. Represent each variable by a separate node. Use the property that value of the variable represented by a node is an algebraic sum of all the signals entering at that node to simulate the equations. Coefficients of the variables in the equations are represented as the branch gains joining the nodes in a signal flow graph. Show the input and output variables separately. Complete the signal flow graph. Supposing I want to obtain a signal flow graph from a block diagram. Name all the summing points and takeoff points in the block diagram. Represent each summing and takeoff point by a separate node in the signal flow graph. Connect them by the branches instead of blocks, indicating block transfer functions as the gains of the corresponding branches. Show the input and output nodes separately if required to complete the signal flow graph. So given a signal flow graph as shown in figure 6.12, so what we have to do is we have to represent S1, T1, S2, T2 as nodes, and we have one branch for the input, the gain of 1, one branch of 1 for the output with the gain of 1. And now what we have is we have an arrow from S1 to T1 with a gain G1, and we have from T1 to S2 two gains, one is G3 and the other one is G2, From S2 to T2 we have one G4 and a feedback loop minus H2, and from output to S1 we have one feedback loop minus H1. The equivalent transfer function for a signal flow graph is obtained through what is called as a Mason's gain formula. According to the Mason's gain formula, the overall transfer function is equal to sum of Tk delta k by delta, where k is equal to number of forward paths, Tk is the gain of the kth forward path, delta is equal to system discriminant and can be calculated as 1 minus summation of all individual feedback loop gains including self loops plus summation of gain into gain product of all possible combinations of two non-touching loops minus gain into gain product of combinations of three non-touching loops, and so on. And delta k is the value of delta by eliminating all loop gains and associated products which are touching the kth forward path. So this we can understand using one of the examples. So in figure 6.14 we show a signal flow graph. In this particular signal flow graph, first thing we need to do when we have a signal flow graph is to find the number of forward paths. So G1, G3, G4, G5 and G6 is one forward path. Let us call it T1. So likewise G1, G2 and G6 is another forward path. Let us call it T2. The next step is to identify feedback loops in this particular signal flow graph. One of the feedback loops is L1, which is minus G4 into H1. The other one is minus G3, G4, G5 and H2. And then there's a third loop, L3 is equal to minus G2 into H2. Now what we need to do is find the value of delta. Delta is equal to 1 minus sum of individual loop gains. So L1 plus L2 plus L3. Now what we need to do is we find out which of these are non-touching. So L1 and L2 are touching, so we don't take that. So we take L1 and L3. So what happens is the overall formula for delta is equal to 1 minus L1 plus L2 plus L3 plus L1 L3. Now for delta 1, eliminate L1, L2, L3 as all these are touching, and so delta is equal to 1. For delta 2, eliminate L2 and L3 as these are touching to L2 from delta. So now you will get delta 2 is equal to 1 minus L1. So the overall transfer function is T1 delta 1 plus T2 delta 2 by delta. And if you really substitute the values of T1 and delta 1 and T2 and delta 2, you will get the overall transfer function as shown in the slide. Take another example. This is the signal flow graph where G1, G2, G3, G4 is one forward path and G1, G2, G5 is another forward path. The loops involved are L1, which is minus G1 into H1, L2, which is minus G3 into H2, L3, which is G1, G2, G3 into H3, and L4 minus H4. So now what we do is take combinations of two non-touching loops. So you get L1 into L2, L1 into L4, L2 into L4, L3 into L4. Using this, what you do is you calculate the transfer function of delta, and then if you really want to find delta 1, it is equal to 1 as all loops are touching, and if you want to find delta 2, all loops are touching, so you can find out the overall transfer function. Take another example. In this particular example, we have two forward paths, G1, G2, G3 and G4, and G1 and G6, G1 and G5 rather, and the transfer function is summation k is equal to 1 to 2 Tk delta k by delta. So what are the feedback loops? L1, G1, G2 into minus H3, G2, G3 into minus H2, G4 into minus H1, G5, H1 into H2. This is a tricky example because there is a possibility of missing out L4. Now we found out delta is equal to L1 plus L2 plus L3 plus L4, L1, L3. So delta is equal to 1 minus minus of G1 G2 H3 minus G2 G3 H2 minus G4 H1 plus G5 H1 H2 plus G1 G2 G4 H1 H3. For T1 all loops are touching, so delta 1 is 1. For T2 all loops are touching, so delta 2 is 1. So transfer function is T1 delta 1 plus T2 delta 2 by delta. By substituting the different values, I can find out the overall transfer function. Now you consider another example. In this particular example, the number of forward paths is 2. So G1, G2, G3, G4 and G5 and G4. So what is the transfer function? Summation k is equal to 1 to 2 tk delta k by delta. So T1 delta 1 plus T2 delta 2 by delta. So there are three feedback loops here. L1 which is minus G2 into H1, L2 G1, G2, G3, G4 into minus H2 and G5, G4 into minus H2. So delta is 1 minus L1 plus L2 plus L3 plus L1, L3. When you substitute the different values, you are going to get the value of delta as shown in the figure. Then what you have is delta 1 is equal to 1 because all loop gains which are touching the forward path are eliminated, and then delta 2 is equal to 1 minus L1 which is 1 plus G2 into H1. The moment you replace T1 and delta 1 and T2 and delta 2 and delta with their equivalent values, you will get the overall transfer function. Now you consider another example. In this particular example, what we have is only one forward path, which is G1, G1, G2, G3, G4 and G5. And what we have is we have individual loops L1 minus G1 H1, L2 minus G3 H3, L3 minus G1, G2, G3 and H2, and G4 minus G4 into H4 and minus G5 into H5. So what are the combinations of non-touching loops? L1 and L2, L1 and L5, L1 and L4, L2 and L5, and L3 and L5. So if I take combinations of non-touching loops, I get three non-touching loops. I'll get L1, L2 and L5. So delta is equal to 1 minus L1 plus L2 plus L3 plus L4 plus L5 plus L1, L2, L1, L5, L1, L4, L2, L5 plus L3, L5. And then when it take the combinations of three non-touching loops, you need to take a minus sign here. So minus L1, L2 and L5. So delta is 1 plus G1 H1 plus G3 H3 plus G1 G2 G3 H2 G4 H4 G5 H5 G1 G3 H1 H3 G1 G4 H1 H4 G1 G5 H1 H5 G3 G5 H3 H5 G1 G2 G3 G5 H2 H5 G1 G3 G5 H1 H3 and H5. So now if I want to find T1, delta 1 is equal to 1. So what is happening is, what is the overall transfer function? T1 delta 1 by delta. So G1, G2, G3, G4, G5 by delta. By substituting equivalent values of delta, I can obtain the overall transfer function. Likewise, you can solve for all other different types of problems which are shown in these slides as you go along. Some of the problems are simple, others are more difficult. All it needs is practice.